In this video, we're going to go over another example of determining whether a sequence converges or diverges. So we'll be looking at this sequence on the left. And remember, what a sequence is an infinite list of numbers. And intuitively, the way I think about sequences converging is the terms really far out in that sequence or the terms really far out in that list. If they all start looking identical, then we call that sequence convergent. The terms really far out all start looking exactly the same. All right, let's take a look at this sequence that we have. So with sequences, since these are infinite lists of numbers, the mathematical tool that helps us ask the question of what the terms really far out in the list look like is our limit. So we take the limit as n goes to infinity of the sequence function. So in this case, 5n cubed plus 2n to the 5 over 2, all over 3n to the 2/3 minus 4n cubed. And of course, at this junction with any sequence, we're really taking the limit. And if that limit is finite and exists, the sequence converges to whatever that value is. So that we can use all the tools from limits that we know, things like L'Hopital's, doing some algebra. And just for practice in this particular problem, I'm going to try to take us the algebraic route to try and cancel some terms off to make this limit a bit simpler for us. Okay, so let's take a look at what we have. I'm just going to move this over just slightly. So what I mean by algebraically is we're going to first look at what's in the numerator and then what's in the denominator. In particular, we're going to be looking at the highest power term in each, the numerator and denominator separately, and we're going to factor that out of each term. So for example, out of the numerator, the n cubed is the larger n power term. So what we're going to do is try to factor an n cubed from that numerator. So I'll just do this in the next line. So if I factor out an n cubed from the first term, we just get an n. From the second term, well, I'm just going to put this as 2n to the 5 over 2, the original thing we have, all over an n cubed. So you can kind of see that if we multiply this n cubed into both of these terms, how that second term cancels out the n cubes to arrive back at the original 2n to the 5 over 2. And we're going to do some cancellation on it in a moment. But let's do a similar thing for the denominator now. So looking at the denominator, the larger n power term is in the 4n cubed. So we can just, again, factor an n cubed from both terms in the denominator. So if we go ahead and do that, that second term just becomes a minus 4. While that first term, I'm going to do a similar thing to what we did in the numerator. Write it as the original 3n to the 2 over 3 divided by an n cubed. So you can see that if we were to distribute that n cubed from outside into that denominator, we would arrive back at the original thing we started with. But more importantly for us right now, you can see that those n cubes sitting in front of the numerator and denominator, those two things are going to cancel out. So we can rewrite what we have here in the limit. So in the numerator, we have a 5 plus a 2n to the 5 halves. And now since we have that n cubed in the denominator, we can rewrite that as multiplying an n to the minus 3rd power. And we're going to do a similar thing in the denominator now. We can write that as a 3n to the 2/3, the original term. But then since we have that n cubed in the denominator of that fraction, or of the fraction in the denominator, we can multiply by an n to the minus 3rd. And the reason we're going to go ahead and do that is just so we can see how we're going to do some algebraic simplification in a moment. Because we have n terms raised to different powers, we're going to be able to add those powers together to simplify. So the next line, just doing that simplification, we have 5 plus 2n. And again, since we have n's to the different powers being multiplied, we can add their powers together. So we have n to the 5 halves minus 3, or n to the minus 1/2. In the denominator now, we have a 3 times n to the 2/3 times n to the minus 3. We can add those powers together, and what we're going to get is a n to the minus 7/3. Minus 4. So let's take a look at what we have. And now whenever I'm dealing with negative exponents, particularly in limits, I always like just making that term into a fraction. So in the numerator, we can write this as 5 plus 2n, or sorry, 5 plus 2 over the square root of n, taking that n downstairs because we have the minus power. And in the denominator, we can write this as a 3 over n to the 7/3. Minus 4. Now, the reason I think this is helpful is, remember, we had this limit as n is going towards infinity. So in these two terms, the 2 over square root of n, and the 3 over n to the 7/3, those denominators of those two fractions alone are getting really, really large. So as n goes to infinity, this fraction is looking like 0. And same with the fraction in the denominator. Both of these terms are looking like 0 in the limit because their denominators are getting really, really large. So at the end of the day, what this limit looks like as n goes to infinity is a 5 over minus 4, or a negative 5/4. So remember, this was a sequence. So taking the limit here really said, hey, what do those terms really far out in the sequence all look like? Do they all start looking like the same thing? And in this case, they all start looking like the number negative 5/4. So we would say that the sequence converges to minus 4 or minus 5/4.